Well, welcome back to another video. Well, in this lesson, in this video, we're going to talk about polynomial functions. Grade 10, section 3 of chapter 2. Perfect. We already got familiar with polynomial expressions and how to add, how to subtract, how to evaluate a given value to a polynomial, and how to multiply and how to divide, and how to equalize to polynomial, this kind of stuff. We already studied all of them in the previous 2 lessons of this chapter. And today we're going to talk about polynomials function. Well, in polynomials function, perfect. This is in the beginning of this lesson, I would love to give you some examples regarding to the polynomial functions. For instance, here is a quadratic function, x squared minus 5x plus 3. There is a cubic function here, and there is another expression. There is another function that its degree is 5. So these are examples of polynomial functions. All right. So in order to get familiar with the lesson, I would love to give you this kind of examples in the very beginning of the lesson in order to remind you what was the polynomial function. Remember, it says from the beginning of the first section, we just defined it and we said that it's the sum of some simpler terms. For example, x squared minus 5x plus 3. So this polynomial consists of 3 terms. And as well as this one consists of 4 terms, and here we have got 5 terms. So these are examples of polynomial functions. So the first lesson, the first thing that we to study is how to find zeros. We just make sure that the video is going well, perfect, the design and everything is perfect right now. So find the zeros of polynomial functions. How are we going to find out whether a number is a root, is a zero of a function or not? So here, perfect, a. So a is a number, is a zero of the function f of x, then f of a would be equal to 0. So what does it mean? It means that if a, which is a number, is a zero of a function, of a polynomial function, when we evaluate that a into action, the result must be equal to 0. Must be. Be careful. Perfect. So it means that at the same time, x minus a becomes one of the factors of the function. The converse is also true. Perfect. So let's just define this paragraph completely. It says fa is a zero of the function f of x, then f of a, which means by evaluate that number to the function, the result must be 0. That is the meaning of zero of a function. And at the same time, x minus a, x minus that a that we have got, would become a factor of that polynomial function that we have. Perfect. Right? And the converse is also true, which means that if x minus a is a factor of the given polynomial, so in that case, x equals to a would be a zero of that polynomial function. Perfect. So always to find the value of x, equalize x minus a to 0. All right. So instead of whenever the factor is given, we need to equalize it to 0, and that value that we are going to find out for x would become the 0 of the function. Just like this, just do this kind of thing that we said on this example. The type of example, the type of question that it is going to come for this year's exam, for this stage, which is grade 10 book, it's going to be in this way. But let me just make you sure that, let me talk about the importance of this section for grade 12. That is one of the essential information and essential topic for grade 12 regarding to polynomial function, finding the zeros and this kind of stuff. Perfect. So is this expression x plus 5 a factor of the function of f of x equal to x squared plus 2x minus 15? So is this expression x plus 5? Here it says that always to find the value of x, equalize x minus a to 0. So what do we have here as x plus x minus a? So we have got this factor. Let me just bring my pen. Perfect. So yeah. So I guess red is more clear. So our factor here is x plus 5. X plus 5. It says always equalize it to 0. So we need to equalize it to 0 to see what we are going to get. So move this 5 to the other side. It's going to become x equals to negative 5. So we got the value of x, which is the 0. Let's see whether it's going to, if that's negative 5, if we evaluate this negative 5 into our function, our polynomial function, and the result was 0, then we can claim that x plus 5 is a factor of this polynomial. So let's see. Let's just evaluate it. F of negative 5 equals to, instead of each x, I need to put negative 5. That is the meaning of evaluating. Perfect. So negative 5 all square plus 2 times negative 5 minus 15. All right. So negative 5 powered by 2, it's equal to 25. All right. 2 times negative 5, it's equal to negative 10. And we have got a negative 15 originally. So right now, 25 minus 10, 15. 15 minus 15, the result is 0. So we can say that since by evaluating negative 5 into our polynomial function, the result becomes 0. So we can say that x plus 5 is a factor of this function. That is the meaning of like this solution. I'm going to repeat it in order to make it clear. So since it says the question x plus 5 is a factor of this function or not, based on this note, we need to equalize that factor to 0 in order to find the value of x that we need to substitute it and replace it into the x. Okay. We substituted and the result became 0. If the result becomes 0, then it means x equals to negative 5, which is x plus 5 is a factor of that polynomial function. Let's go to the next question and see more questions, more stories regarding to zeros. Is the expression x minus 2 a factor of the function or not? Is this a factor of this polynomial function or not? So in order to find out whether it is a factor, we need to do what? The first step, equalize that factor to 0 to find out the value of x. So x minus 2 equals to 0. Move this negative 2 here, so x would give us 2. That is the value of x. Now substitute it into our function. So f of 2 equals to 2 powered by 2 minus 3 times 2 plus 2. So 2 powered by 2 it's 4, minus 3 times 2 it's 6, plus 2. So 4 minus 6 it's equal to negative 2, plus 2, the result is 0. So we're going to say that since the result becomes 0, x minus 2 is a factor of this function. That is the meaning of being a factor of a polynomial function. Perfect. The next question here, again the similar idea. It says, is the expression x plus 3 a factor of this function or not? Let's just find it out whether it is or not. So the first step is equalize this factor to 0 to find out the value of x. So x plus 3 equals to 0. 3 comes to this side, so x equals to negative 3. X equals to negative 3. So what do we need to do with this negative 3? We need to replace it into x, substitute it into our function in order to find out whether we will get 0 or not. If we got 0, we will say that okay, x plus 3 is a factor of that function. If we didn't get 0 and something else, then we cannot say that x plus 3 is a factor of this polynomial function. Let's just substitute it, okay? F of negative 3 equals to negative 3 powered by 2 plus 2 times negative 3 minus 3. So negative 3 powered by 2, you know that it's equal to positive 9. All right. Then 2 times negative 3, it's equal to negative 6, and minus 3 originally is over there. So 9 minus 6, it's 3. 3 minus 3, it's 0. Since the result is 0, we will say that x plus 3 is a factor of this polynomial function. Perfect. I hope that this story is understandable and clear to you. guys. So let's see whether we have got different examples or not. Fortunately, we do. Is the expression x minus 2 a factor of this polynomial or not? The title is the same for all these type of questions, but the thing that you need to do is just two steps. First of all, equalize the factor to 0, minus 2 equals to 0, then find out the value of x, which is 2 here. Move these negative 2 to the other side, it's going to become positive 2. Then substitute it into our polynomial. So f of 2. Instead of each x, put the value that you have got. So 2 powered by 3 plus 2 powered by 2 minus 2 times 2. Perfect. So 2 powered by 3, 8. 2 powered by 2, it's 4. And negative 2 times 2. So let's see, 8 plus 4, it's equal to 12. Minus 2 times 2, 4. 12 minus 4, it's 8. Since we didn't get 0, so we are going to say that x minus 2 is not a factor of this polynomial. Okay, it's not a factor of this polynomial. Why? Because we did not get 0. Let's just check it again. So we got x as 2. So substitute 2 here. 2 powered by 3, it's equal to 8. 2 powered by 2, it's equal to 4. Negative 2 times 2, it's equal to 4. So 8 plus 4, 12. Minus 4, 8. We did not get 0, so it's okay. It's not a factor of this polynomial function. Okay. Next question, it says that, is the expression x plus 3 a factor of this function or not? Let's see. So, first step is equalize x plus 3. Okay, x plus 3 equals to 0. Then find out the value of x, so it's equal to negative 3. All right. So, substitute this negative 3 into our function. Okay, so f of negative 3 equals to negative 3 powered by 4 plus 3 times negative 3 powered by 3 plus negative 3 powered by 2 plus 5 times negative 3 and plus 6. Let's see what we are going to get. Okay, let's just change this color in order to make it more clear. Okay, red. Negative 3 powered by 4, if you go and check it, it's equal to 81. Negative 3 powered by 3, it's equal to negative 27 times 3, it's equal to negative 81. Okay, so go and check a negative 3 powered by 3, since it's an odd exponent, the result is negative 27 multiplied by 3, negative 81. Now the next one is negative 3 powered by 2, the exponent is even, so the result would be positive 5 times negative 3, negative 15 plus 6. First of all, these two are going to cancel each other, 0. 9 minus 15 is equal to negative 6, and plus 6 is equal to 0. Since the result became 0, we're going to say that, okay, x plus 3 is a factor of this polynomial function. That's it. That is regarding to the story of a factor of a function. So it needs two steps. Equalize the factor to 0, and then substitute the value that you have got into our polynomial function. If the result became 0, you're going to say that, okay, that expression is a factor of this polynomial function. If the result became something different than 0, you're going to say that it's not a factor of this function. Okay, so right now we're going to talk about details of some types of functions graph. Remember, we had 4 of them while we talked about degrees in the beginning of this chapter. So right now we are going to talk about the graph of the functions. The first one is constant function. Constant function, it means that when we have, let's say, let me just bring the pen here, because since I stay over there, so I need it here. Okay. What is the color? Red. Perfect. So the first one is constant equation or constant function. Let's say f of x equals to 5. Our function equals to a constant term. That is a constant function, by the way. So its domain is R, from negative infinity to positive infinity. I already said that domain works like on x-axis. So imagine, so let's just here, let's say f of x equals to 3 in order to match this one. So just like this one, that is our coordinate plane. Here is 2 and here is going to be 3. So f of x equals to 3. That is the graph of f of x equal to positive 3. So as you know, that as you can see, the domain is from negative infinity to positive infinity. Okay? From the lowest x, let's say, to the greatest x. Domain related to x coordinate. Okay? Perfect. X-axis. And how about the range? The range is exactly one number, which is that number that the function equals to. For example, here, f of x equals to 3. So the range would be only that number. Only that number for constant function. Be careful. So right now, for f of x, domain is going to be all the real number, and the range would be only 3. All right? And the constant function, it's just like this. By the way, for constant function, actually, like we can give you some different examples, but at the end, if we have time, I will definitely mention some more examples regarding to constant function. But you just better know that constant function is when f of x equals to just a number. So that number can be positive, it can be negative, it can be 0. All right? Always domain of constant function is all the real number, which is from negative infinity to positive infinity, and its range equals to only that number that the function equals to. Okay, so here the second function is linear function. So in linear function, the degree is 1. You better know that. In grade 9, you just define it in this way, that you said y equal to mx plus b. You call that m slope, b was y-intercept, and x and y are variables. Perfect. So as you can see, degree is 1 for all these variables that you have it. That's why we call it linear function. In linear function, because I'm gonna just sorry. Okay, domain is for linear function. Let's just come back to linear function. Here, it's defined in this way: ax plus b. Still, it's the same. So a is the slope, b is the y-intercept. Well, for linear function, domain is all the real number again, and the range is also all the real numbers. Wait a second. Okay, so for linear function, as you can see, take a look at the graph of it. It has a slope, but the domain of linear function is all the real number, because it's from like the very, very lowest point, which is from the negative infinity, to the biggest point, which is from like to positive infinity. And its range as well. So range depends on y-axis, as you can see here. So the lowest exponent, the lowest number, the lowest value is negative infinity, and the greatest value is positive infinity. So imagine that you have got a linear function. Let's say, let me just give you one example here. Let's say we have got y equal to 2x minus 5. That is a linear function. Okay, for linear function, domain and range, both of them are always all the real numbers. That's it. So because we can give every single x, every single value of real numbers to our function, and for each value we will get a different outcomes. That's why when we have a linear function, we will say that domain and range of our linear function is all the real number for both of them, domain and range. Perfect. Let's go to the next question, next graph, next type of question. It is quadratic equations. There is an interesting story regarding to quadratic equation. So its general formula, it's in this way: ax2 plus bx plus c. That is the general formula of quadratic equation. Right now, it somehow depends on the coefficient of x, which is a. If a is positive, it's going to be open up the graph. The graph would be open up, just like this one. And if it is negative, if a is negative, the graph would be open down. All right, just like here. Okay. So that's gonna change the story of range. Again, in quadratic equation, in quadratic function, it's better to say quadratic function. In quadratic function, domain is always over real number. Okay? Because we can give every single value, every single point of real numbers to our function. But the range will depend on like the graph, because we said that it starts from the lowest value, lowest y to the greatest y. So it changed based on the function. It changed. All right. So here, as I already said, that domain of quadratic function is all the real number, but range, it starts at its lowest point and continues upward towards infinity. If it is open up, it starts from the lowest value, lowest, here it says lowest point, which is from like based on the parent function of quadratic function. The range is from 0 to positive infinity. But if it is open down, it's like from negative infinity to the greatest value, which is based on the parent function, it's 0. But as I said, we have different examples, and it's going to change the story regarding to the range of the quadratic function. So let's just summarize it in this way. If you have quadratic function, if a was positive, a is the coefficient of x squared. If a is positive number, so it's going to be open up the graph. If a is negative, it's going to be open down. That is the first thing that you need to know regarding the quadratic function. The second thing is, domain of quadratic function is always all the real number, from negative infinity to positive infinity. But range, based on the question, will change. But the idea of range is from the lowest point to the greatest point. If it is up, open up, the range would be from the lowest point to positive infinity. If it is open down, the range would be from negative infinity to the greatest point. That is all about domain and range of quadratic function. Okay, let's move to the next function, see what we have. We have got cubic function. Well, in cubic function, as you can see here, okay, let's just come back to the cubic function before go to the quartic function. Okay, in the cubic function, we said that, by the way, these two are the graphs. So the blue one and the red one are both cubic functions graph. But if you better know that there is a note here, domain and range of odd degree polynomial function is all the real number. Again, I'm going to repeat it. If you have a function, a polynomial function, and its degree is odd, just like linear function, its degree was 1, 1 is odd. So since it's odd, domain and range of that kind of function would be both all the real number, and from negative infinity to positive infinity. So for cubic function, since it's a function with degree 3, and 3 is an odd number, so in that case, domain and range of cubic function would be just like the linear function, like both of them are going to be all the real number. Okay? So when we are going to have the blue graph, when the coefficient of x squared is x cubed is positive, so we are going to have, by the way, the general form of like cubic function is ax cubed plus bx2 plus cx plus d. Okay, something like this. Since the degree is 3 and it's odd, Domain and range, both are going to be all the real numbers. That is the first thing that you need to know about the cubic function. And if A is positive, that's going to be the graph. If A was negative, the graph would be something like this, in this way. And for both cases, by the way, domain and range are all the real numbers. The graphs are very important. I hope that you have a view of them in your mind and keep it until grade 12 because you need the graphs. The next graph is quartic function. So quartic function is just like somehow the quadratic function, the graph. We have got ax4, which is the degree is even. So when the degree is even, domain is all the real number, but range depends on the function. Range will change. If A is positive, what is A? A is the coefficient of x4. Since we have got quartic function, so we should have a degree of 4. So the coefficient of that variable that it has degree of 4, if it is positive, the graph would be open up. And if it is negative, the graph would be open down. So we said that domain of quartic function, just like quadratic function, is all the real number, but the range depends on the function. So it's simply, we will say that it starts when it is open up, just like this graph. It starts at its lowest point and continues upwards toward infinity, because it goes to infinity. Okay. And when the coefficient of x4 is negative, domain is still R. It's all the real number. But the range would be from negative infinity towards the greatest value of the graph. Okay, so from negative infinity, it goes up until the greatest point of the graph. Perfect. So find the domain and range of the given function. We have got some types of functions here. First one, since the degree is 2, so it's quadratic function. Quadratic function. So it is quadratic function. For quadratic function, we said that domain is all the real number. Domain is all the real numbers. But the range, how are we going to find out the range? Well, if you go and graph that function, either by point plotting method that we already studied, go back to the absolute value lesson, we studied point plotting method, or transformation like methods, transforming like based on these steps that we had it regarding to the absolute value function. Go back to that section. We said that we had a table for transforming like the parent function. So the parent function of quadratic function is y equal to x squared, and its function is something like this. That is the parent function for quadratic function. Okay, in case if you want to do it by like transformation method, so you can just go ahead in this way. Otherwise, you can use point plotting methods. All right. So here, like give some points to the function and take like the outcomes and then graph them. Okay. I mean, plot them on the coordinate plane. You will definitely get the graph of the function. Okay. Or transformation. So that is the parent function. It says +1. So it's not. There is no bracket. The changing number is out of the x squared. In that case, we need to go vertically. We need to move vertically. If it is positive, go up. If it is negative, go down. So here, it's +1. Imagine +1 is here, so the graph would be something like this. Okay? And here, domain is all the real number, but the range is, look, from the lowest point. The lowest point is what? +1. So, and it's closed, by the way, +1 to the greatest point. So the greatest point is what? Positive infinity. And in infinity, we have got always open interval. All right? Great. So it's open up. Why? Because the coefficient of x squared is positive, which is positive 1. So it's open up. All right? I hope that it is clear. And how about here? So it's a linear function. Linear function. So simply for odd degree function, domain is R, and the range is, again, all the real numbers. Okay, the next one is a constant function, because f of x equals to only a number. So in that case, we said that domain for linear function, constant function is always R. And the range is exactly only that number, which is 10. So you can just put it inside a bracket like this. So therefore, when we have constant function, domain is R. When we have constant function, the range would be exactly that number that the function equals to, which is here 10. But I would love to give you some more questions regarding to the first one, which is quadratic functions. So just come here. Imagine if you have f of x equals to x minus 1 all square, and f of x equals to x squared minus 2. How are we going to find out the domain and range of these two? So basically, when we have quadratic function, when the degree is 2, it means we have got quadratic function. In quadratic function, you better know that domain is always R. Domain of the function is always all the real numbers. Perfect. So we don't care. Our problem is not about the domain. The range is our problem. So let's just graph these two functions by using transformation method. All right. So transformation method say that, okay, let's just transform it based on the parent function. The parent function is something like this. That is the graph of y equal to x squared. What graph do we have here? It's x minus 1 all squared. Since the changing number is inside the parenthesis, inside the bracket, so we need to go horizontally. If here is negative, go right. If it is positive, go left. So since there is negative, move to right for 1 unit. So here, imagine here is 1. So that is the graph of y equal to x minus 1 powered by 2. Domain is all the real numbers. The range is from the lowest point to the greatest point. So the lowest point on y-axis, be careful. Range depends on y-axis, y point. So on y-axis, the lowest point is what? 0, and it's close by the way. So the range, I'm going to write range here for that function is from like 0, and it goes up boundlessly, okay, until positive infinity, open interval. How about the next one? Well, in the next one, let's use blue. We don't have any bracket, it's x squared, and minus 2 is out of x squared, okay, out of the bracket. There is no bracket by the way here, but actually the bracket is here. Since no need to put a bracket for x, we did not. Negative 2 is out, so we need to go vertically, either upward or downward. Since the operation is negative, so we need to go down. All right. For how many units? So 2 units. So negative 1 is here, negative 2 is here, and since the coefficient of x is positive, it's open up our graph. So it's going to be something like this. Great. That is the graph of y equal to x squared minus 2. All right. So the range of this one would be from the lowest point on y-axis. Be careful, please. So it's equal to from negative 2 closed to positive infinity. That is the story of finding domain and range of quadratic function. I hope that it is clear. One more example regarding to what if the function was open down. So in that case, the coefficient of x squared must be negative. All right, let's say if f of x equals to negative x squared plus 6, or f of x equals to negative x minus plus 2 powered by 2. Let's time of the video. Let me just check it. 5 minutes long. Becomes longer because of this one. Okay, negative x squared plus 6, negative x plus 2. Okay, there is a coordinate plane here. The parent function, let's just draw it with blue. That is the parent function, which is y equal to x squared. So right now, quickly, since you know that transformation, negative x squared, since it's negative, so it's up and down, all right? And it's plus 6, so let's say 1, 2, 3, 4, 5, 6, so it's going to come here. Okay, we will reflect it with respect to x-axis. That is going to be the graph of y equal to negative x squared plus 6. Okay, how about the next one? There is a negative, so it's going to be up and down, our graph. Okay, take this one as a note. X plus 2, the change is inside the bracket, the parenthesis. So it's going to be, since it's positive, we need to go to left. How many units? 2 units. So negative 1, negative 2, let's say. So the graph would be something like this. Remember, since it's inside the changing number, so we need to go horizontally, either to right or left. How can we find out that it is to right or left? If it is positive, go to left. If it is negative, go to right. So here the domain of both of them are like all the real numbers. But the range for the first one is from the lowest, remember the black one, y equal to negative x squared plus 6. So from the lowest point, which is it goes to negative infinity, be careful, negative infinity, to the greatest point, which is positive 6. Be careful, negative infinity, always from the least to greatest, you will make your intervals. How about here? So the red one is again from negative infinity to the greatest value of y-axis, which is 0. That is the story of domain and range of quadratic function. I hope that this kind of questions that I gave it to you in my own will be like helpful and fruitful, inshallah. So I will leave these questions for you. I hope that you can solve them by yourself because I already solved. So it's quadratic function. You can just draw its graph. It's linear function. Both domain and range are all the real numbers. It's constant function. In constant function, domain is all the real number, and the range is exactly that number, equals to that number, which is negative 11. I already solved the question. Okay, we have got some questions, some graphs. Based on the graphs, we will decide like what is the domain and what is the range. Here, okay, let me see what is the question. Perfect. Okay, when the direction of a polynomial function's graph, when the direction of the polynomial function's graph within its domain goes upward and then change direction to go downward. So when it goes, let me just bring my pen. Okay. Within its domain, which is from negative infinity to positive infinity on x-axis, from left to right. Don't forget, from left to right. When the direction of our graph goes upward and then change downward, so in that case, our function is going to have a local maximum. That is going to be the maximum, the local maximum. So right now we are going to define extremum of polynomial function. Extremum points are local maximum and local minimum. Both of them are included in grade 12. So try to learn it right now and make it easy for the rest of this journey that you have in front of yourself. Okay. When the direction of a polynomial function's graph within its domain goes upward, when it goes upward and then goes like downward, it has a local maximum, and vice versa in its interval. However, if the direction of the polynomial function's graph within its domain goes downward and change direction to go upward, the function has a local minimum value in its interval. So let's just check whatever is written here on these two graphs. As you can see here, we have got in the first one, we have got a local maximum. Why local maximum? Because it says that if our direction of the graph, of our polynomial functions graph, like goes upward and then change downward, okay, in that case we are going to have a local maximum. So as you can see, in local maximum points, that is the local maximum point, which is x equals to 2. That value is like greater than all the values around itself. Okay, for example, the value of here, let's say it's 3. So it's greater than all the values around it. As you can see, so the around 3 here, these points are 2, 2.5, and this kind of stuff, 1, 0, -1 for the other side as well. And the greatest outcome here is 3. Therefore, we call this point local maximum. Okay, how about the next graph? Let's just analyze the next graph. Okay, from left to right, when we move, it goes upward, and then here when we reach here, it goes downward. So it goes upward, it goes downward. So we are going to have a local maximum again. We're going to have a local maximum at that point. But if you come to this point, the graph here, it goes downward and then it goes upward, down, up. Look, down, up. So we are going to have local minimum in that case. Let's just make it like more clear. If we go up and then down, we have local maximum. If we go down and then go up, we have got local minimum. That's all about this story. Okay, let's just see how it's going to come in the question in grade 10, by the way. Okay, by the way, before doing that, we need to talk about like increasing and decreasing intervals, functions. So increasing, suppose a and b are two numbers within the domain of the function, a and b. Imagine if the function, if the domain of the function is all the real numbers, we are going to take two numbers, let's say a and b. Okay, if b is bigger than a, and f of b also was bigger than f of a, in that case we are going to say that our function is increasing in that interval. Okay, again I'm going to repeat it. If we have two numbers within the domain of a function like a and b, if b was bigger than a, and in that case like f of b also was bigger than f of a, in that case we are going to claim that our function is increasing. But if we have the same thing, like again b was greater than a, but f of a is bigger than f of b, in that case we are going to say that our function is decreasing. So increasing, suppose a and b are two numbers within the domain of the function f of x. If a was less than b, then f of b was greater than f of a. Both of them are the same, which means the function is increasing on that interval. Okay, if the function, if we have got 2 points and one point is bigger than the other one, and f of that point, for example here, b is bigger than a. So if f of b was bigger than f of a, then we are going to say that we have got increasing function. Okay, perfect. And let's just come to these 2 points. So here, as you can see, let's just take 0 and 1. So 1 is bigger than 0, right? 1 is bigger than 0. And f of 1 and f of 0. Let's just compare these two. F of 1 equals to 2. And f of 0, it's exactly 0. So f of 1 is bigger than f of 0. Then in that case, we are going to say that our function is increasing in that interval. And as you can see, from left to right, the function is increasing. Okay. And okay, let me just check the video. Sorry, there was an interruption. Okay, let's just continue from increasing and decreasing. That is the second part. Decreasing. Suppose a and b are two numbers within the domain of the function f of x. If b was greater than a, and then f of a was greater than b, here b is greater than a, but here vice versa, f of a is greater than b. Since they are opposite, we are going to say that the function is decreasing. Okay, so let's just say it again. If we have two numbers, if we take two numbers like within the interval, within the domain of a function, just like a and b, these a and b are going to be numbers. Okay, if b was greater than a, in both cases, increasing and decreasing, always b is greater than a. But if f of b was greater than f of a, just like b greater than a, and if both of them were the same, in that case we are going to say that the function is increasing. But if b still greater than a, but f of a is greater than f of b, in that case we're going to say that the function is decreasing. Just like here, come and let's just try it here, as we already did 0 and 1. So it was increasing. As you can see from left to right, it's increasing. All right, since it's increasing, so look, f of 0 was 0, f of 1 it's equal to 2. 1 is greater than 0, and also f of 1 is greater than f of 0. So the function in that interval is going to be increasing. Okay, how about if we take negative 1 and 0, negative 1 and 0. So you know that 0 is greater than negative 1, right? But not 0, actually it's going to be increasing yet. Let's say, okay, 1 and 2. So 1 and 2. So everybody know that 2 is greater than 1, right? 2 is greater than 1. But f of 1, and we have got f of 2 here. So f of 1 equals to what? Positive 2. And f of 2 is equal to negative 2. So here is positive 2 and here is negative 2. So of course f of 1 is going to be bigger than f of 2. Since they are opposite, 2 is greater than 1, but f of 1 is greater than f of 2. Then in that case, we are going to say that our function is decreasing. Perfect. Of course, you need more examples. Let's see the examples. What do we have? Okay, the title of the question. It says use the graph to determine the extremum point, local maximum value, and local minimum value, domain, range, and increasing and decreasing intervals. So based on that function, we can definitely see that domain is all the real numbers, from negative infinity to positive infinity on x-axis, as well as the range is all the real number, from the negative infinity goes up until positive infinity. From negative infinity to positive infinity. Perfect. Then it says, find the local maximum. So find the extremum points means local maximum and local minimum. So the local maximum is here. What was the definition of local maximum? Go up, then go down. Change direction to go down. All right. So here is local maximum. Okay, so the local maximum value is, by the way, 4, but if it asks for the point, so the point of, let's just do it here, local maximum is the point -1 and 4, and as well as the local minimum is here. It goes downward and change direction to go upwards. So that point would become the local minimum. So local minimum as it is clear, it's the minimum point, by the way, the minimum value in this interval. All right. So in that case, we are going to say that, okay, it's 1 and 0. The point, x is 1 and the value is 0. Perfect. Then what it asks about too, like domain, range, local maximum, local minimum, and increasing and decreasing interval. So increasing and decreasing interval. For increasing and decreasing interval, we have like different interval. For example, from always we move from left to right. So let's just write increasing interval and decreasing interval, decreasing interval. For increasing interval, from left to right, if it goes up, so it's increasing interval. From negative infinity, it goes up until negative 1. So from negative infinity, it goes up until negative 1. All right? Then open interval. Why? Because when we write increasing and decreasing, we need to write like open interval, as it's like local maximum, or you can just write closed interval. Since 1 is included, 1 is closed here. So and from negative 1 to positive 1, from left to right, it's decreasing. So from negative 1 to positive 1, it's decreasing. Okay? And then from 1 to positive infinity, again, it's increasing. So from 1 union, from 1 to positive infinity, it's increasing. By the way, we are going to say that when we are going to determine like increasing and decreasing points, always we need to put open interval for like the point, that increasing and decreasing point. That's why here I want you always to write the increasing and decreasing intervals in open intervals. Always, when you want to determine increasing and decreasing intervals. Perfect. Because of the local maximum and local minimum, the boundary points are not going to be like with closed interval. Okay, determine domain as well as increasing, decreasing intervals of the function f of x equal to x squared minus 4x plus 5 within x equals to 0, x equals to 1, and x equal to 3, x equal to 4. How are we going to deal with this type of questions? So first of all, it says determine the domain. So only domain. It didn't ask for the range. What kind of function is this? Quadratic function. So domain would be all the real numbers. So domain is not a problem here. Then it says find increasing and decreasing interval. So increasing interval and decreasing interval. Okay, for increasing interval, we need to find f of, look, 1 is greater than 0. Let's find out f of 0 and f of 1. So f of 0 and f of 1. See which one is going to be bigger. So f of 0, substitute 0 into our function. 0 squared, 0, minus 4 times of 0, 0. So 0 minus 0, 0, plus 5. So f of 0 is 5. How about f of 1? 1 squared, 1, minus 4 times 1, negative 4. So 1 minus 4 plus 5. 1 minus 4, negative 3, plus 5, it's equals to 2. So which one is bigger? Of course this one. So right now we say that 1 is bigger than 0, but f of 0 is bigger than f of 1. So that means opposite. So since we have got opposite, like between the point the inequality of the point and the equality of the result. So we are going to say that in that interval, our function is decreasing. Like in the interval, like from 0 to 1, f of x is decreasing. Decreasing. Okay, let's just check the next one, 3 and 4. So everybody know that 4 is greater than 3, right? But let's just find out f of 4 and f of 3. F of 4 was bigger than f of 3, we are going to say that, okay, in this interval, which is from 3 to 4, the function is increasing. But if f of 3 was bigger than f of 4, again, we are going to say that our function would be decreasing in this interval too, just like the previous one. Okay, let's find out 4, f of 4. So f of 4 is 4 squared 16 minus 4 times 4, 16. Plus 5. So 16 minus 16 is equal to 0. Plus 5, it's 5. So f of 4 is 5. How about f of 3? So 3 squared 9 minus 4 times 3, it's equal to 12 plus 5. So 9 minus 12, negative 3. Plus 5, it's equal to 2. So f of 4 is bigger than f of 3, just like the points. Since 4 is bigger than 3, and f of 4 is bigger than f of 3 too, so we are going to claim that our function, which is f of x, would be increasing in this interval. Which is, so we're going to say that in the interval 3 to 4, f of x is increasing. That's it. This is how we are going to find out the increasing and decreasing points. Perfect. So the next question, I hope that you understand this one, guys. Let's just go to the next question. Again, we are going to deal with this graph. With a graph, determine local maximum value, local minimum value, domain, range, increasing and decreasing interval of the function in the given graph. So in this graph, as you can see, domain is all the real numbers. And the range is also all the real numbers. Why? Because it's an odd degree graph. So the domain is, this function continues, by the way. It's from negative infinity to positive infinity on x-axis. And on y-axis, we have got the same thing. It goes down continuously, and it goes up as well as continuously. Okay. So domain is all the real numbers. Range is all the real numbers. Okay. That is regarding to domain and range. And local maximum and local minimum are easy to find out. Take a look at the graph and see which point. Look, from left to right always. From left, it's increasing, then decreasing. So that is exactly the definition of local maximum. So local maximum is the point is 1 and exactly 2. And the local minimum is, look, take a look at that point, around that point. It goes down and then it goes up, the direction of the f of x. So at that point, when it changed the direction, goes down, goes up, in that point we are going to have local minimum, which is, the point is 3 and negative 2. That is the local minimum point. Perfect. Then what else? So increasing and decreasing. As you can see based on the graph, ladies and gentlemen, take a look at this graph. So from left to right, always you need to consider the graph from left to right. From the left to right, so from negative infinity until 1, it's increasing. So increasing interval is from negative infinity to positive 1, union, as well as from this point, it's increasing until positive infinity. So what is that point? 3. From 3 to positive infinity. Perfect. And the decreasing one decreasing interval is, look, from left to right if we move, so from 1 to 3, our graph is decreasing. Okay, so decreasing interval would be from 1 to 3. As you can see here, if we move from left to right, from this point, which is 1, the graph would be decreasing until 3. That's why the decreasing interval is from 1 to 3. That is how we are going to find out decreasing and increasing intervals for a given function, for a given graph. The next one, let's see what question do we have. Again, something like that. So we have got a different graph, but here, be careful. Domain and range are like limited. So from this point to that point. So the domain is, let's say here 1, 2, 3, negative by the way. And here 1, 2, 3. So 1, 2, 3, positive. So the domain is from negative 3 closed, it's closed by the way, to positive 3 closed. And the range is from lowest point. The lowest point here is almost negative 4.5, and the greatest point here on y-axis, y-axis, it's almost equals to 4.5. So from negative 4.5, both of them are closed by the way, till positive 4.5. Okay, great. So the graph is limited by the way. Then it says local maximum and local minimum again. So local maximum and local minimum are clear. This one from left to right again, it's moving downward, and in that point it changes the direction, goes up. So it is the definition of local minimum, because it goes down and goes up. So it's local minimum. Go back to the definition of local minimum. So local minimum, I will write LM instead of like writing local minimum. So the point of local minimum is that point, which is negative 2 and negative 2 and negative 4.5, negative 4.5. That is the point of local minimum. How about the local maximum? So I would write local max, not get confused with local minimum. So local maximum is here. Take a look at the direction of the graph from left to right. From left to right, when we move, it's increasing, and in that point it's decreasing. From that point, when we move from left to right, it's like moving upward. Then in that point, it changes the direction down to downward. So in that point, which is 2 and positive 4.5, we have got local maximum points. And the increasing and decreasing intervals. So increasing, I will just write increasing interval is from negative 2, it's increasing until positive 2. So from negative 2 until positive 2, it's increasing. And for decreasing interval, we have got two intervals. From negative 3 until negative 2, the graph is decreasing. And as well as from positive 2, from left to right we move. From positive 2 to 3, the graph is decreasing. So we can show this one in this way. From negative 3 to negative 2, union from positive 2 to 3. In these two intervals, our graph is decreasing. Perfect. And I hope that it is clear and understandable, guys. Next question, let's see whether we do have it or not. This question, I will just leave it as a homework. Determine local maximum value and local minimum value. Domain range increasing and decreasing interval of this function f in the given graphs. So find all of them and then write the answers in the comment, share it. I'm going to check it for you. Thank you so much for listening to me, and I hope that we see each other in another video. Take care of yourself.